Hello everyone, and welcome to the final lecture of the course CSEC 513, Lightweight Cryptography for the Internet of Things. This final lecture is about side channel analysis. Of course, this is not a topic that we can cover in a single lecture. Actually, it should be there should be a single course for the topic of side channel analysis, but of course, this is not my specialty, so I will try to give some basic definitions and some basic examples. So for this reason, I actually focused on a course that was given by Stefan Mangard. The course was titled Secure Implementation of Cryptographic Algorithms. So these slides that I'm going to use are very shortened versions of the slides that Stefan Mangard used in his lectures. So these are just basic definitions and some basic examples to give you the idea behind the side channel analysis. So let's start. So we should first talk about embedded systems. An embedded system is some combination of computer hardware and software that is specifically designed for a particular function. Recently, embedded systems have become more and more complex and are close to the functionality of a PC, for example, smartphones, and with the advancements in Internet of Things, we can have, for a very cheap price, we can have embedded systems or devices that have a lot of functionality. So today's embedded systems are different than the ones that were used 10 years ago. Many side channel attacks focus on small embedded systems where all components that are critical for the security applications are integrated on a single piece of silicon, and these include RAM, flash memory, etc. So this is the main idea. So we have a very small device that has its own RAM, flash memory, and so on. So it is just a piece of silicon that performs the functionality that is required for its purpose. Attacks on systems with multiple chips can be performed in similar ways and are typically simpler. So it doesn't matter if there is more than one chip. Integrated circuit market, we will short it integrated circuit as IC. More than 5 billion devices per year, but again, this slide is a few years old. So with the Internet of Things, I think this number should be more than 10 billion now. So I don't have a updated number about this information, but you can guess that it is still a lot. In general attack scenarios, we only assume that the communication channel is insecure and the attacker can eavesdrop. So this was the whole idea behind this lecture. So when we were talking about cryptographic algorithms like lightweight block ciphers, hash functions, stream ciphers, we always assume that the communication channel is insecure. So somebody can eavesdrop, and if there's an active adversary, maybe they can modify some bits or add or drop some bits and so on. So this was always the general attack scenario. But in side channel analysis, the situation is a lot different than this. In case of embedded systems, the attacker often has more power. For example, let's see the examples that were given by Stefan Mangard. Let's think about pay TV. The broadcasting company gives smart cards to customers. Customers may try to duplicate the cards. So you have the device to yourself, so you have a physical access to the device. This is why we say that the attacker has more power now. We are not only listening to a communication channel and capturing a ciphertext. Now we have the device. And let's see more examples similar to this. Electronic purse. The customers might want to add more money themselves. Digital rights management. The customers might want to copy the material for their friends. So if you buy a video game, music, or anything from the internet, you have generally they have digital rights management, DRM, and you're not supposed to give it to other people. Brand protection, the customer wants to use cheaper ink, batteries, etc. So some companies want to prevent this kind of situation. etc. So when designing an embedded system, it is necessary to assume that the customer will try to break it. And this is always the case. So even when you're writing a software, you have to assume that people will try to find a bug in it. So you have to think every possible scenario to overcome problems. So in this case, we are giving the device to the people. So we should be prepared about what they can do. So generally, the easiest thing that comes to mind is that since there are some cryptographic algorithms inside these devices, these smart cards or chips, etc., when you give it to the customer can, somehow cut it, open it, and look at the ROM and see what the secret key is that is used in cryptographic algorithms. So this is the general idea, but these devices are built as a tamper-proof. So when you try to open it, the device deletes everything in its ROM. So this is why we call them tamper-proof. So this is why capturing a device would not be enough to get the secret information. So this is important. A lot of people think that once they get the device, they can get everything inside it, but this is not the case. For instance, if you get an Android or iPhone, mobile phone, so if it has a full disk encryption and the secret key inside the device, but this doesn't mean that you can get the secret key and decrypt every data. But of course, it should be implemented in a good way. So tampering is not, we assume that you cannot tamper with the device. You cannot get the secret key directly from device ROM or its data storage. But having a physical access gives you a lot more power, because now you can look how the device works and gather some information from it, and this way you can capture maybe the secret information. So this is what we are going to talk about in this lecture. Attacks on embedded device can be as follows: social engineering, this is always possible; logical attacks, these include software vulnerabilities, API attacks, and more importantly to us, cryptanalysis. So all of these attacks are applicable to almost any scenario. You can find a weakness in the cryptographic algorithm, so you can cryptanalyze it and break the system if it is designed in a bad way. But most of the time, modern ciphers are secure. So these are the things that you can perform. But more importantly, you can perform physical attacks. So you can observe and manipulate physical properties of the device or its environment. So modifying its environment, this way you might force the device to work in a wrong way, let's say. So this is why most of the time we see side channel analysis as a physical attack. Of course, most of the time we assume that you have physical access to the device, but for some attacks you don't need to be there physically. For instance, if you are performing a catch timing attack, you don't need to have the access to the device itself. So you can maybe perform this attack on a cloud service. You don't need to be in the server room, but from a distance, if you have access to the catch and you can measure the timing of this catch operations, then you can capture secret information. So here's an example. You find a USB stick with secret data on it. To access it, you need to enter an 8-digit PIN. Device has a delay response, so one trial takes 1 second. So this is almost always the case for this kind of devices. You cannot try a lot of pins or keys in a very short time. Brute force requires 10 to the 8 seconds because there can be at most this many different pins, so you try one by one. But if each trial takes 1 second, then this many seconds would be around 3 years, and you cannot try this attack for 3 years. So question is, can you better than this? So since you have the USB stick, you have physical access to it, and the answer is yes, you can. So let's see what can be done. So most of the time, the side channel analysis does not break the algorithm itself. It doesn't break the cryptographic algorithm. Most of the time, it breaks the implementation. So, for instance, AES is a secure cryptography block cipher, but when it is implemented on an embedded device, you can break it if it is implemented in a bad way. And this is why side channel attacks are important. So let's look how we assume that this is implemented in an ARM processor. So assume that password check is implemented on an embedded ARM processor in a straightforward way. So it works like this. It checks the correctness of the first digit. If it is correct, then it checks the second digit. If it is correct, it checks the third digit, and so on and so forth. But in its check, if the first digit is not correct, then there is no point on checking the remaining digits. So the device does not allow you access. Thus, execution time is directly proportional to the number of correct pin digits. So this is important, and actually this attack also works on padlocks. So assume that you have a padlock, the basic ones, these locks has most of the time have 3 digits. So there are like 1,000 different possibilities to open these padlocks. And you can attack that physical padlock like the idea here. So what you do is you try to pull the lock to yourself. Since the pin is not correct, you wouldn't be able to pull it. But you start rolling the top digit, which has 10 possibilities. When you reach to the correct one, since you are pulling to the other side, when you reach to the correct one, it kind of loosens up. So this way you know the first digit. You do it for the second digit and so on. So you get the correct one in at most 30 trials instead of 1,000. So this is the thing you can do here. So what you do is you select a random pin value, fix all the digits except the first one, measure the timing for all 10 possible values for the first digit. The value that leads to the longest execution time is the correct one. Set the first digit to this value and proceed with the next digits in the same way. This way you try at most 10 times 8 tries, which is 80, to access to the USB stick. If the timing measurement is noisy, averaging over multiple measurements needs to be done. So this is identical to my physical padlock example. Instead of 10 to the 8, you perform 10 times 8 trials, and this way you can break the system. So here what you are performing is a timing attack, because you are looking how long it takes to check a pin value. If it takes long, this means that you get the first digit correct. If it takes short time, this means that it is wrong. So how we can prevent this? Checking every digit of the entered pin is not a solution, because code requires more operations to be performed when a digit is correct. So assume that the designer of the USB stick inserts NOP instructions to balance the timing of both execution paths. NOP is no operation. So even if the first digit is incorrect, it performs a NOP, so it takes the same time. So it doesn't matter in this case if the password is correct or not. So first digit is correct or not, doesn't matter. The timing will be the same. Question is, how can we attack such a fixed system? And the question is actually, can we attack now? But the answer is yes, we can break still. We can perform different attack